Okay, so I'm going to start by labeling up the forces in this on this diagram before I even start attempting the question. So on this particle, I have 15G as a force down. I have tension this way. On this one, if I read it, it says there is a smooth horizontal plane. Okay, so this means there is no friction. So there's no force this way. We have our T this way. I also might want to just label on the 10G down and reaction normal this way. This is just a good habit to get into and will help us in further questions. Now, my acceleration, which way is it going to go? Well, I think, having a look at this, it's going to go this way. Okay, so this one's going to move down and this one's going to move right. Okay, right, now we can have a go at the question. So we've all labelled up the acceleration and the tension, so these kind of go together in a bit of a simultaneous way. So I'm going to write an equation for this lower particle first. So this one's going to be 15G minus T equals 15A. Okay, the second particle, which is this one, we've got T going to the right. We've got no force, so we've got zero resistive force, so it's T minus 0, and that equals 10A. Okay, got a simultaneous equation. If we combine them together, if I add them, the T's are going to cancel, so I end up with 15G on this side. On this side, I have 25A. So my acceleration is going to equal 15 over 25G, or more simply, it's going to be 3/5 G, which is perfect as an answer, or you could write it in decimal, which is 5.88. Okay, so there's your acceleration. For your tension, let's use one of these. I'm going to use the second one because it's really, really easy. T equals 10A. So quite simply, I can times my acceleration by 10. So I get 30 over 5G, which is 6G, or in decimal is 58.8 newtons. Okay, so there's part A, there's part B. What modelling assumptions have you made? Well, the assumptions you've made, we're told that it's a frictionless cable, but what it doesn't say is that it's light and inextensible. So cable is light, has no mass, and inextensible, so no stretch. For this type of question at the end, it's almost always an answer like this. You have a kind of stock list of answers, light and inextensible, or it might be something like frictionless or air resistance, things like that. Okay, but when you have a final answer like this, it's usually a 1 marker, and it's usually one of the modelling assumptions or modelling sort of parameters that we've already discussed. Okay, so as before, I'm going to start by labelling up my diagram. So here we go. I'm going to call this tension here T1, and I'm going to call, the tension between A and B T2. Okay, just to clarify that they're going to be different tensions. Okay, we don't need to worry about friction, but it's always good to get in the habit of drawing your weights and your reactions. Okay, so let's change to black. There we go. Tension between the particle B, this one, and the 10 kilogram mass. Okay, well, let's work this through. It's released from rest. So let's write an equation for this one, which is going to be 10g minus t equals 10a. And for b, we're going to have, well, sorry, not for b, but for this whole section, we're going to lump these together. So we're going to put a and b together as if they are an 8 kilogram mass. Now that works because this cable here is inextensible, so we can consider these two to be a single particle. So this one's going to be T, there's no resistive force, so it's going to be T minus 0, and that is going to equal 8A. Okay. Now, we just want the tension, but we need to, the easiest way of doing this is to find the acceleration first. So let's add these together as we have done before. So we have 10g equals 18a. So our acceleration is going to be 10 over 18 or 5 over 9, so 5/9 g. Then what I can do is I can put that back in to the second equation. So the second equation is t equals 8a. So I do t equals 8 multiplied by 5/9 g. By leaving it in fraction, we make our life a little bit easier. It's going to become 40 over 9g. Which in decimal is 43.6 newtons. Okay, so that's kind of a standard, use two equations to find our tension. We don't really need our acceleration, but it's kind of quite a standard way through, and often questions will ask for acceleration, so that's all good. So that's A dealt with. Tension between A and B. Okay, so slightly different now. What I'm going to do, and you can do one of two things. You can either isolate A or you can isolate B. I'm going to isolate A because I think the calculation is going to be easier. So we have 4 kilograms. The tension in this direction is T2. That's what we're trying to find. The resistance to motion is 0. There's no friction. And we are accelerating. Now, it's good that we found the acceleration because we're going to need it now. The acceleration is 5/9 g. So our equation is going to be T2 minus 0 equals 4 lots of 5/9 g. So T2 equals 20 over 9 g, which is 21.8 newtons. So that's by isolating particle A. I could do the same with particle B. I'll just show you that really quickly. So I could have particle B. I could have T2 in this direction, T1 in this direction, 4 kilograms, and my acceleration this way. And this way, what I'd do is I'd say, okay, I have T1 minus T2 equals 4A. And if I do this, it rearranges to T2 equals T1 minus 4 times 5/9 g. T1 is 43.6. This is 21, isn't it? 21.8. So therefore, by doing it this way, I get the answer of 21.8. Okay, so it doesn't matter which one I isolate, I get the same answer in both cases. Okay, so you can't really go wrong. It's up to you which one you choose. What I would say is choose the one with fewest forces on it. So A has only got 1 force on it, whereas B has got 2 forces on it. Okay, but overall, our T2 is 21.8, whichever way you do it. Okay, so in this question, yet again, we're going to start by labelling up. And the first thing I'll say is that I know it doesn't say it in the question, but we're going to assume that this mass A has a a mass of A kilograms and B is B kilograms. I wasn't particularly clear on that, but hopefully you've modelled it in the same way. So by that token, we're going to have AG going down here and a tension going up, and we're going to have this one is BG going downwards, Rn that way, and RT is this way. Okay. Now, because it's frictionless, that's an assumption you've made, hopefully, and because of that, the whole system must move this way. There's not going to be a situation when, if it's frictionless, it's going to go the other way, or it's going to stay at rest. Hopefully from the video you saw that we won't get a rest situation. It'll either be a very, very small acceleration or be a larger acceleration. It will never be a zero acceleration, theoretically. So once I've got these in place, I can do what I've normally done. I can write my formula, well, write my equation. So I have AG minus T equals, it's going to be a bit confusing this, but hopefully it's okay, A little a. And for particle B, we're going to have T minus 0, and that equals BA. Okay, now what we'd usually do to find the acceleration is we'd combine these two together, we'd add them together. So let's do the same. We have AG on this side, and on this side we have A plus BA. Now, to rearrange it, let's make our life easier. Let's make it brackets A plus B, little a equals AG. So I have A, the acceleration, equals AG over A plus B. Okay, so I've got a general formula for the acceleration when we have a massive A and a massive B. And actually, this is quite a nice formula because you can put in, you could almost use this to put in whatever values you've got here. As long as it's a frictionless surface, then you're happy. So that's the acceleration. To do the tension, I'm going to use this second one. I'm going to use T equals BA, and I'm going to put my acceleration here in this place here. So I have B brackets AG over A plus B, and that's newtons. I can leave it like that, that's absolutely fine, or if you'd like, you could write AB, AB times G at the top. I've done it that way so we don't write bag. Just, should never write bag. So there you go, ABG at the top, divided by A plus B. That's our general formula for the tension. Okay, so to start with in this question, let's label up our forces. T in this direction, T in this direction, no friction. Okay. Right, now this question's asking us to find at what speed this 4.2 kilogram mass hits the floor. So one of the things you want to find is what this velocity is here. The next thing is at what speed does the particle hit the pulley, which is here. So we can put, if we call that one V1, we can call this one V2. And the last thing is, how long does it take for this particle to reach this pulley? Okay, so we also want the time from here to here. Okay, so we've got a few things to do, but the nice thing is it starts off in fairly kind of familiar territory. So the first thing we do is, at no point do we need the tension. So we don't need to worry about tension, which is good. So we have 4.2G minus T equals 4.2A. And we have T minus 0 equals 4A. Okay, so combine them, cancel out the T's. We have 4.2G equals 8.2A. And this gives us a value, when we divide 4.2G by 8.2, an acceleration value of 5.02. Okay, I'm just going to put that in a box. I'm worried about this becoming a bit complicated to look at, so I'm just going to move this. I'm just going to move this answer slightly and make it a little bit clearer. Okay, so we've got the acceleration. That's great. That's the first part done for this question. We need to know what speed the 4 kilogram particle hits the floor. Okay, so we've got a SUVAT to work with. So we have, if we write out our SUVAT, I'm going to go up here for this, SUVAT. So what have we got? We've got the distance, and that's 1.2. The initial velocity is 0. Final velocity is what we want to find. The acceleration we know is 5.02, and we don't have the time, okay, but we do want to find the time eventually, so let's leave time in there. So let's see if we can find the time and the velocity. So the velocity, I think it's obvious we're going to use v squared, so let's use v squared equals u squared plus 2as, and as often happens, u is 0, so that goes straight away. I have v squared equals 2 times by 5.02 times by 1.2. Okay, so if I square root that, I'm just going to get rid of this. If I square root that answer, I get a value of 3.47 meters per second. Okay, so that's our second answer. The first one requested. So that's the velocity it hits the floor. So we know here now is 3.47 meters per second. Great. Okay. Next thing to think about, how long does it take for this to happen? So how long is it going to take for it to get from here to the floor? Well, because we've got the final velocity now, we could use that in calculation. Now we could use other SUVATs, but let's use a simple one. Let's use v equals u plus at. Let's rearrange it. So if you rearrange it, we get v minus u divided by a. So my time is going to be 3.47 minus 0, so 3.47 divided by 5.02. So my time, when I work this out to 2 decimal places, gives me 0.69 seconds. So it takes 0.69 seconds for it to get from stationary here to the ground, which is helpful. But actually what we want to find out is what velocity this 4 kilogram particle hits the pulley at and how long that takes. Okay. So we've got part of it, 0.69 seconds. So what I'm going to do is I'm going to draw another line which is going to represent the situation on the horizontal plane. So I'm just going to draw another line here. Now we start here, here's our 4 kilogram mass, and this whole distance is 2 meters, remember. So for the first 1.2 meters, which is about here, the particle accelerates, and it's going to take 0.69 seconds to get there, because that's the same time as this particle took to reach the floor. So this is where this inextensible idea comes in. This top particle's got to move the same distance as this bottom particle and at the same speed. So it's going to take 0.69 seconds, and when it reaches this point here, its velocity is 3.47. Now, the question is, how long is it going to take to get from here to here, which is the pulley? And what speed is it going to hit here? Well, the first one we can answer without any calculation. What do we know about this surface? Well, we know the surface is frictionless. and we've also assumed there's no air resistance. So that means that the velocity it hits the pulley at is the same as it was at 1.2 meters. So the velocity is going to equal 3.47. It's not going to slow down. Okay, it can't, because there's nothing stopping it. There's nothing making it slower. So it's going to stay at the same speed, and that's going to be the same speed as it hits the pulley. So the final part of the question is to work out how long it's going to take to travel this final remaining 0.8 meters. And to do that, we just need to use that time is distance divided by speed. Okay, so very, very basic. So distance divided by speed, the time is going to be 0.8 meters divided by 3.47, which is the speed. And that gives me a time of 0.23 seconds. So when I combine them, 0.69 plus 0.23, I get my final answer, which is 0.92 seconds. Okay, so from being released from rest until it hits the pulley, it takes just under a second. And finally, the modelling assumptions we've made, inextensible. So we have light and inextensible cable. Inextensible, and no air resistance. Okay, so for this question, what I've done to start with is I have labelled on the forces here 9G, 5G, and my tensions. Now what's really important is these two tensions are different. Okay, you cannot assume they're going to be the same tension. They're different because they're moving different masses. Okay, now what you could do on this question is you could think about it particle by particle, and that would be fine. That will get you to a solution. And to do that, you'd do something like 9G minus T equals 9A. The next one you'd write T1 minus T2 equals 3A. And the third one you do T2 minus 5G equals 5A. Now that's great, but that gives you a kind of simultaneous equation with three particles. Now it's doable that way, and if you have done it that way, that's absolutely fine, no problem. You will get the same answer as what I'm going to do, but hopefully I'm going to be able to describe this to you in a bit of kind of simpler method. Now the hints at the bottom here, I did include a little hint for you. If you redraw the whole system, now if I just draw it here, if I model it as one particle, that particle is going to have a mass of 5 plus 3 plus 9, so 17 kilograms. Now we need to think about, well, if I bung this all together, what's the overall force? Ignore the tensions because they're gone, because I've squeezed it all together, okay? There's no tensions anymore. I've got all my masses together. What's the force going this way? Well, that's this force here, which is 9G. What's the force going this way? Follow it down, that's 5G. Okay, so I've simplified it by squashing it all together. And to do this, by doing this, I end up with 9G minus 5G, and that equals 17 times A. So this gives me 4G, 17A. My acceleration is therefore 4G divided by 17, which comes to 2.31 meters per second to the minus 2. Okay, so that's simplified everything for us. Okay, remember these are inextensible. So what goes on here is translated here, and what goes on here is translated here. The only thing is the tension in them will be different. Okay, but remember, thinking back to the start of our work with connected particles, what happens to one happens to the other. Now, let's find the tensions. So let's just focus on this particle here, the 9 kilogram particle. So we have 9G minus T, T1 in this case, and that equals 9A. Okay, so T is going to equal 9G, subtract 9 times by 2.31. This gives me a tension, a T1, of 67.4 newtons. for T2, we could choose 3. Let's choose the 5 kilogram one instead, and then use 3 to check. So for this one, T2, or second tension, minus 5G equals 5A. So T2 is going to equal 5 times 2.3 plus 5G. So our second tension, T2, equals 60.6 newtons. Okay? What we can do eventually is we can say, okay, well, this particle, the 3 kilogram particle, must be travelling at the same acceleration, and T1 is bigger than T2, so we do T1 minus T2, that equals 3A. So we do 3 times 2.31. I'll just do that quickly. Which is 6.93. So if I do T1, now remember I have rounded these, so it's not going to be exact, but it's going to be hopefully in the right ballpark. Minus T2, which is 60.6. So 67.4 gives me 6.8. Okay, so we can see, even though we've rounded, I'm going to change these equal signs. There we go. We get roughly the same answer. Okay, it's just a little check to see that it works. Now, these answers are fine. What this does highlight a little bit is that if you round here at 2.31 and you use that rounded figure as I did, then we're going to get inaccuracy in the final answer. However, this is going to happen, and I would expect in the exam they would let you have 7 here. Okay? But yeah, don't overcomplicate it. Remember, zoom out and then zoom in to find the tensions.